Hello. I got to thinking more about this designing an ammeter out of a galvanometer, and I figured y'all might think this little explanation I did at the end to show you that the galvanometer current was in fact linear. In other words, gave it a linear scale. This does show a linearity between the galvanometer and the shunt current, but it doesn't necessarily show you a linearity between the actual current coming in. So I thought I'd try to clarify that a little bit more, just to make sure you understand that it is in fact a linear scale. So let's look at it for a second. What we do know is that IG, the current going through the galvanometer, which was just this little part right here, right, is equal to basically the shunt resistance divided by the resistance that it had, that the galvanometer has, times the shunt current. But again, that's not necessarily the same thing as saying it's the same as the current going into the ammeter. So what we do know is the current in the ammeter is in fact equal to the current through the shunt plus the current through the galvanometer, because obviously it's going to come in, let's say it's 3 amps. When it comes in, it's got to break off to the shunt, so there's I shunt, and then it's going to go to the galvanometer. So just from Kirchhoff's junction rule, we know that that's the case. So what I really want to know is the galvanometer current proportional to the actual ammeter current. So what I'd really like to do is get rid of the IS in terms of, in other words, the shunt current in terms of IG and A. So using that, I can say, well, the shunt current is actually equal to IA minus I galvanometer. So now I can plug that back in here, and I'll get IG is equal to 1 times 10 to the negative 9. Again, these are the numbers from the previous video. So the video where I actually made the ammeter, over 100 ohms. So really, if you wanted to make it a more generic problem, it would be shunt resistance divided by the galvanometer resistance. And then that's going to be times IS. But IS is actually equal to I coming into the ammeter minus I going through the galvanometer. So we've got IG related to IG. So I'm going to distribute all this junk and say this is IG is equal to, notice 10 to the negative 9th divided by 100 is 10 to the negative 11th. So it'll be 10 to the negative 11th IA minus 10 to the negative 11th IG. So if I really want to get IG and see how it relates to IA, I need to pull the IG over here. So I'll have 1 minus 10 to the negative 11th times IG, because the IG had a coefficient of 1. When I pull that over here, that actually becomes plus, not minus, sorry. So plus 10 to the negative 11th times IG, and that's equal to 10 to the negative 11th times IA. So now you can see that IG is just equal to 10 to the negative 11 over 1 plus 10 to the negative 11 times IA. So yes, the galvanometer current is directly proportional to the actual current coming through the circuit. So it is a valid ammeter. That means, for instance, if you have a current of, we designed it for 3 amps. If we have a current of, say, 2 amps, then this will be 2 amps times 10 to the negative 11th divided by 1 times 10 to the negative 11th, and so on and so forth. So basically, a reading of 30 would be 3 amps. A reading of 20 would be 2 amps. A reading of 10 would be 1 amp, so on and so forth. I hope that clarifies, as opposed to obfuscates.